Hello there, mathletes, and welcome back. This is section 1.3 from our text. So before we started graphs of functions, this is mainly going to teach us how to find domain and range when we look at a graph. But I thought first, let's go through and review typical functions, families of functions we call them. So let's do that. So one of the first functions that we look at is just a simple linear function. And here's a graph. And the parent function looks like this. And we can shift it up and down the y-axis by like adding stuff here. I could shift it up 1. I could shift it down to 1, down to here. Let's see. We could also move it right and left, but that really doesn't make sense because up and down would be the same thing with a linear function. But in any event, we're talking again about family of functions. Families of functions. So what you're looking at here is the parent function for a linear function. Let's go to the next screen and let's do a parent function of say a quadratic. Okay, so that's our parent function. And the way this is shaped is, let me draw a graph. Here's my x and y, my y and x. I guess I could label those. And then this graph, the parent function, looks like this. It's a parabola. So that's a little shaky, but this is the parent function for x squared, y equals x squared, or f of x equals x squared. Remember from yesterday's lesson, we said when you just put f of x in place of y, f of x goes in place of y, that's just writing it in function notation. So this is function notation. It's still in function form, solve for y, but function notation just means you put in that f of x or g of x or h of x or whatever letter you choose. All right, let's consider the next one here. I have y equals the square root of x. So what did that parent function look like? So here is our x and our y-axis, and it is 0. Square root of 0 is 0, and it ends up looking like this. It's like a sideways parabola. So if I had written it the other way, if I solved this for x, it would be this whole parabola, sideways parabola. But since we're just looking at this function, y equals square root of x, that is what it looks like. And we'll come back to these two. I think it's in section 5 when we talk about shifting, or no, section 4, shifting, reflecting, and just moving the graph around without changing the graph itself. We're not going to stretch it just yet, but in the next section we'll look at these. So very important to know what these parent functions are. So how about the next parent function? I have y equals x cubed. So y equals x cubed, here is a graph, here's our x, and here's our y, and the graph looks like this. Crosses the origin, and that is the parent function for y equals x squared. All right, let's go to the next one I have for you that we'll see quite a bit. And that is y equals the absolute value of x. So what this looks like is on the coordinate plane, it looks like a V. It goes on both sides. These are supposed to be straight lines. But this is the parent function for y equals the absolute value of x. And once we get to the lesson on shifting up and down and left and right, everything is based on whatever the parent function, whatever the parent function is. So without further ado, let's get on with the lesson. First, we'll look at example 1. This is on page 29 in your textbook. And what I've done over here is done my best to recreate figure 1.18. And it's part of a parabola, it looks like. It has, make this dot a little bigger. It has a closed point here and tops out at 2, 4, and then it comes back down, and there's an open point at 4, 0. So if I were to state the domain of this, that's everything from, let's see, from here to here is my domain. This is a D. And then from, go a different color here, from here down to here, or from here up to here, I should say, is the range of that function. So if I look at the domain, I notice that it can take on the value of 1 in the x direction, but it cannot take on the value of 4. It goes up to 4, but it does not include 4. So if I were to do my domain, do that and match the colors here. So the domain, if I did it in interval notation, goes to 1. There's a bracket here. This is a bracket because it can include the number 1. And when you move to the right, it goes up to, but does not include the number 4. So that is a parenthesis. So this is what we call it's a half open interval. It's open on the top side, closed at the bottom. So this is interval notation, kind of easy to write it that way for this particular picture. If we go and look at the blue, the range, let's see, in the bottom, at the bottom, it's in the y direction. It can take on the value of -5, and it goes up and it goes to here, so it can actually take on the value of 4. So -5 to 4, including -5 and 4. So this one is a closed. So -5 up to and including 4. So this is a closed interval. It's closed on both sides, so that's a closed interval. This is open or half open, some people would say, and this is a closed interval. So half open, closed intervals. This is based on example number 1, page 29, looking at that picture. All right, let's look and see what else we can discover. All right, so example 2, page 30, I wrote the page number down. It just says find the domain, and it gives this function. So we looked at something like this from yesterday, from 1-2. So it was a square root, and all we need to remember is I cannot take the square root of a negative number. So that means that x minus 4 has to be greater than or equal to 0, because it could be 0, because the square root of 0 is just 0, but it can't be negative. It can't be less than 0. So that would tell me that x has to be greater than or equal to 4. So a couple of ways that we've talked about doing this, I could say all reals greater than or equal to 4. So that's one way of writing this. Another way to write this is in interval notation. Oops, that was a crooked 2. So it could start at 4. So a bracket, and go to infinity. And infinity always gets, I keep pausing my thing. So one way, all reals greater than 4, greater than or equal to 4, or interval notation, which I don't like that interval notation, so I'm going to rewrite it. Get a better That's my infinity symbol. Looks like an 8, sideways 8. All right, and then the third way that we wrote this was, Jiminy Crickets, I keep pausing that. 3. I could say the domain is equal to the set of x, an element of the reals, such that the x is greater than or equal to 4. So oftentimes it will say, if it gives a direction, it'll say use an interval notation. But you can say all reals greater than or equal to 4 if it doesn't, explicitly ask for this. And like I said, most students, including me when I was a student, aren't fond of writing the set notation. So there goes example number 2. All right, so here's example number 2, and we talked about this in lesson 1.2, and it's about the vertical line test. So vertical line test. I'll write that up here. And the reason it's called the vertical line test is if you drop a vertical line on a graph, and I'll drop a blue. So if I dropped it on A rather, this is graph A, notice that it crosses in 2 points. It crosses here and it crosses here. So we would say it fails the vertical line test. And when it fails the vertical line test, then we know this is not a function. So not a function. So jot that down. Now, if we move over to picture B that's in the book, it shows just dropping a vertical line here. It only crosses in one section. It crosses right here. So this is a function. It passes the vertical line test. So we'd say function, function. So that is what they're talking about in example number 3. So let's move on to the next example. All right, now let's look at example 4. It's on page 31. What they're talking about is increasing and decreasing functions. So that means the function value is increasing or decreasing. So one of the pictures looks like this. It has a graph, and we'll draw the picture. Goes up like this. And we would say that this function is increasing. Let's see, we'll do 2 colors here. It's increasing here. So I'd say it's increasing from negative infinity up to 0. And then it turns into increasing again. So it's increasing again there, up here, from 0 to infinity. So what did we do with our 0? Well, if I'd have drawn my graph a little bit better, it kind of is flat right on the origin. So it doesn't increase or decrease at the origin. Got my parenthesis. So it's increasing from left to right, except with the exception of 0. All right, let's go and look at the other picture. The other picture looks like this. Picture B. So that graph goes up and down and back up. So it looks like something like this. So we would say that from here, this is the point they labeled 1, 2, negative 1, 2, and this point is 1, negative 2. So this is increasing, let's see, increasing here and increasing here. So I would say that this is increasing. I'm going to abbreviate increasing. So it's increasing from negative infinity. And remember, we always do a parenthesis here for infinities, negative infinity and positive infinity. And it goes up to, looks like x is negative 1. And again, this is a open interval here. Oops, open interval. Because at the top of this graph, this is neither increasing nor decreasing, right? It's just flat across there, okay? You're going to love these in calculus. So the other thing this does is it decreases from here to here. Whoops, I forgot my other increasing interval. So it increases also from 1 to infinity. Now for decreasing, this guy decreases from, let's see, the -1 down to +1. I'm forgetting my parentheses there. Okay, so let's make this parenthesis look a little better. There, that's better. All right, so again, to recap, we're increasing from -infinity, like coming from left to right across this graph. It increases from -infinity up to -1, up to -1 this way. And then it decreases from -1 to +1 because the graph is going downhill between -1 and +1. And then from 2 to infinity, this graph just keeps increasing. And let me know in the comments down below if you're on YouTube, if you have a question on that. But look at C now. So C is kind of a funky looking graph. It comes up like this, and it kind of pauses at 0, 1, and then it goes straight across to 2, 1, and then it angles down. Let me make my x-axis a little bit longer there. All right, so increasing from here to here, it's not doing anything in here, it's flat, and then it's decreasing from 2 to infinity. So 2 to infinity, remember, we're looking in the x direction. So from -infinity to 0, this graph is increasing. And then from 2 to +infinity, this graph is also decreasing. So let's see, we've been doing increases in yellow. So it's increasing from -infinity to 0. And then we switch to blue. It is decreasing from x equals 2 to infinity. So again, remember, these are not function values. These are x values. So this is what it's doing in the x direction. All right. So let's button this one up. And so now we're talking about what they call relative max and relative min, or relative maximum. Relative maximum. I'm writing that on top of the graph because the 2 points here are relative maximums. Okay, and what makes that a maximum is it's increasing on one side but decreasing on the other. So that makes this a maximum. Here we're increasing to the left but decreasing to the right. So that's a maximum or a relative maximum. When we look at the bottom of the graph, switch colors here, we are looking at 2 relative minimums. So relative minimums. I'll write that in there. Relative minimum. So this is a relative minimum because it's decreasing from the left and it's increasing on the right. Same with this. It's increasing on the left, but it's decreasing on the left and it's increasing on the right. So when it has different function behavior on both sides, that's what makes it a minimum or a maximum. And I just noticed I forgot an E here. So identifying those it's not too hard to do that. In class, we will do on the graphing calculator, show you how to figure out what these are exactly. Next year in calculus, 11th graders, you'll be able to do it without any effort whatsoever. It doesn't even require a calculator. All right, that is it for relative max and min. All right, next up is the step function. Also, no, it's actually the greatest integer function, but we call it a step function. You'll see why in a second. So when I graph this, I'm going to start with 0. Every time I go up in my x value, I don't jump until I get the next integer. So there's an opening here, but everything in between here would get shaded in because 0 is still the greatest integer between 0 and 1. Then we start to move here, and at 2, we jump again. So the greatest integer from here to here is still only 1. It doesn't become a 2 until we get to the 2 down here in the graph. And then the same thing happens. You get to 3 and so on. So you're starting to see probably why it's nicknamed a step function, although it's technically the greatest integer function. So and that comes from the left as well. So -1 is an integer, but no numbers less than 0 to -1 are greater than -1. There's no integers. The next integer is up here. Let me use my pointer. Up here at the 0. And then it goes until it hits the next integer and then jumps. It goes till it hits the next integer and jumps. So it just keeps doing this, and it ends up making kind of a stairway pattern. And that's why, again, it's called the step function. Looks something like this. And this is the domain of the step integer function is all real numbers, right? -infinity to +infinity. I can put any number in place of this. And this little like double, it's like a bracket, but it's got 2 lines. That is what means we're doing the greatest integer function. And these you can graph on your calculator as well too. So that can be demonstrated in class. All right, so let me know in the comments if you have a question or comment about the step function. All right, odd and even, or even and odd functions. So now we're looking at example 9 on page 35 in the book. And the easiest way to explain it at first is to show pictures. So an even function is symmetric on the y-axis. Let me write that. Even. Symmetric on the y. Symmetric, I'm going to abbreviate symmetric. Symmetric about the y. An odd function we say is symmetric, and I'm going to abbreviate symmetric again, but it's symmetric about the origin. So this graph up here, top left, use my pointer, this graph is an even function because it's symmetric on the y-axis. So we'd say that's even. All right. When we move to the right here, this graph is symmetric about the origin. Means I could turn it 180 degrees and it would look the same. So this we would say is an odd function. All right, let's go down to D. Let's look at this one here first. This one is, notice it's symmetric on the y-axis, so we would call that an even function. So that one is also even. But when we come over to this graph, this is C on page 35, it's symmetric, but it's not, it's symmetric about this line right here. Draw a dotted line. That's not the y-axis, so it's neither odd nor even. So that's what we would say. Neither, or neither, however you say it. Neither even nor odd. So just because we have these classifications at even and odd doesn't have to be even or odd. It can be neither of them. So there you go. In class tomorrow, I'll show some examples of how to figure this out algebraically, but it's not too bad graphically. So there we go. So that is it for lesson 1.3. So let me know in the comments below if you're watching it on YouTube what questions you might have, or send me a text on my Google Voice or whatever, however you want to get in touch with me. Okay, so that is it. Thank you for watching, and I'll see you for 1.4.